Today uh, we are going to discuss few problems on systems of particles and rotational dynamics. So before we proceed to discuss problems, let me say a few things. And first thing is, problem solving is very important, not necessarily from the point of view of competitive examinations. Just to understand the subject, one needs to do problems. If a person is not able to solve problems and he or she is able to reproduce only the theory, then that knowledge is not very sound. And Feynman used to call such a knowledge as fragile. For example, a glassware looks very beautiful, glossy, very costly also perhaps, but if one drops it, the whole thing has to go to the dustbin. And so solving problems is very important. I need not emphasize, but however I stress it. And now, while you solve problems, what are the things one needs to take care? It only comes by practice and experience. We are discussing this particular topic on systems of particles and rotational dynamics. We will see gradually various things, and okay, we will go problem after problem. Now, I am going to describe mostly the situations, the physical situations. Then we will see how to solve these problems. And okay, so there is a wire which is in the shape of a parabola. Wire bent in the shape of a parabola. The axes are given here. This equation is y is equal to kx square, where k is a constant. It has to be positive, otherwise the parabola won't look like this. And there is a bead which is kept on this wire, which it can slide along, and it can slide along without friction. Slide along the parabola, wire bent in the shape of parabola, slide along without friction. That is important. Okay. Now, what happens is that the wire is accelerated in this direction with a constant acceleration A. The wire is accelerated parallel to the x-axis. The wire is accelerated parallel to the x-axis with acceleration yeah. So find the new equilibrium position. Question: to find the new equilibrium position. Position of the bead. Okay. Now, if this is stationary, if this parabolic wire is stationary, then the particle will come and settle down at the origin. That is the equilibrium position. Now, what happens? This is given an acceleration parallel to x-axis. Therefore, the bead will slide up. What will happen is at any position there is this mass. Then therefore this mg acting downwards. It can be resolved along horizontal and vertical components. Right, we will do that. So let us say this is a position, and this is the tangent here. mg is acting downwards, and this normal reaction would be perpendicular to this tangent, right? So this mg can be resolved along this direction and this direction. Okay, mg's. So what you have is that this is this n is resolved like this. N is n cos theta. This is n sin theta. Horizontal is n sin theta. So the normal reaction is resolved along these two directions. If this is theta, then this is theta. So n cos theta and n sin theta. This is MA. Okay. So it is a normal reaction at this point, which is resolved along x-axis and y-axis. Right. Now the equilibrium, the particle will be in this new equilibrium position provided when the forces balance and for equilibrium. So it is a mechanical equilibrium. For equilibrium of the particle, we need this n cos theta is the vertical component of normal reaction. So this n cos theta must be equal to the weight acting downwards, weight on the bead, then the weight of the bead. Then next is n sin theta. This is a horizontal component of the reaction. This must be equal to the force with which which is acting on this bead, MA. Now these are the two equations we have. Divide one by the other and you will get 2 by A by G. So this is equation 2 divided by equation 1. So this is theta, this is the tan, this theta here. Therefore tan theta is nothing but derivative at this point, derivative on this curve at this particular point. Therefore dy by dx is equal to y is equal to kx square y is equal to kx square. Therefore dy by dx is equal to 2kx. This is equal to tan theta. Therefore x is equal to tan theta is acceleration divided by acceleration A on the particle or acceleration of this wire divided by acceleration due to gravity, that divided by 2k. Because for tan theta I have substituted, and so therefore this is the new equilibrium condition. Now we spent few minutes on analyzing this problem. What are the various things that are expected from the student to know? So whenever a problem is given, the student should ask this question: why this particular problem has been given? Of course, if you do it correctly, and then you may get selected in that particular exam. That's not what I mean by this. What I mean is that what are the concepts which the examiner is testing. So the examiner expects the students to know certain concepts to get qualified. And in this problem, that is being tested is, does the student know the conditions of equilibrium? Number 1. That means the forces should balance. That is number 1. No external torques. That is number 2. Then after that, this is also somewhat mathematical, because one needs to know that at this particular point the slope can be obtained by differentiating this. Okay. The next problem which we are going to ask is this on angular velocity. Okay. Let me explain this problem. Now sometimes when you read a problem, it strikes some kind of fear, but you have to patiently look at it and divide it into various components. Here in this particular problem, what happens is that there is a circle. Okay. We have axis. This is the axis. That's not very important to label them. And then what we have is a particle is going round. a particle is going around on this circle. My God. Here. A particle is going around this particular circle. Now, what are the things given? This is given. The particle is going around the circle with angular velocity is 5 radians per second. And then R, the radius of the circle is 4 meters. Right. Now, what is happening is I can draw the from this particular point. This is the foot of the perpendicular. P prime is the foot of the perpendicular on this x-axis. P prime is the foot of the perpendicular on the x-axis. Now, as the particle goes around the circle, the foot of the perpendicular will go back and forth on this x-axis. Now people would have recognized this is what you say, the one-to-one correspondence between circular motion. The particle which is going on a circle, it has got circular motion, whereas the foot of the perpendicular will have simple harmonic motion. But even all these things are not necessary to do this problem. What are the things which have been asked? One, to calculate the speed of the foot of the perpendicular. Foot of the perpendicular. That is, we calculate the speed of P prime. When OP sweeps 30 degrees. That is, theta is equal to 30 degrees. 30 degrees with respect to sweeps. Theta is equal to 30 degrees. So, when the particle is here, what is the speed of this P prime? That is the question asked. The problem is very simple. This I will call it as R. Therefore, OP prime is equal to x into cos theta. Right? OP prime is equal to x is equal to r cos theta. Now, x is a function of time because it keeps varying. Dx by dt is equal to minus r sin theta d theta by dt. D theta by dt is what is omega, minus r sin theta minus r omega sin theta. So this is the now foot of the perpendicular. V is the velocity, P at P prime, the modulus of that. This is going to be equal to modulus of r is 4 and omega is 5, that into sin 30. Okay, this is equal to 10 meters per second. This is 10 meters per second. Now, another thing. Here itself. I will call this point as Q. This is Q. Now, what is the angular velocity of P? Angular velocity of P, you are required to calculate. Angular velocity of P about point Q. And what we are doing in this, given the omega is 5 radians per second is the angular velocity with respect to O. Now you are asked to calculate what is the angular velocity with respect to Q. Right? This is again a very fairly simple one, even though it looks very daunting. All that you need to do is that join this card. This is a card. I will call it as M, let us say. Okay. So this card PM subtends an angle theta. Therefore, now we need to calculate what is the angle. This is the, okay. So all that we need to calculate is calculate the angle. Required angle is equal to MQP. This we know very well. This is a chord in a circle. At the center it subtends an angle theta. Therefore it will subtend half of that angle at any point on the circumference. This is equal to theta by 2. In this case it is going to be equal to, it is omega is 5 radians per second, 5 by 2 is equal to 2.5 radians per second. So a simple property of circle is made use of. Similarly, you can calculate what is the acceleration of P prime, that you can calculate. Okay, there are various things. Once you go about doing a problem, ask what are the various other things which you can calculate. We will do a problem on center of mass. So this is on center of mass problem. This again I have taken this problem from a competitive examination. So problem is like this. A uniform circular disc of radius r. Okay. From this disc what is happening is another circular disc of radius r by 2 is removed. Okay. This is so this circle is radius of the smaller circle is r by 2 obviously, and this center I will call it as O. This as another point I will call it as D. So from the bigger circle the smaller circle is cut out and it's a uniform circular disc. Okay, now what is the task is you have to calculate what is that to calculate, to determine the center of mass of the remaining portion once this has been removed, of the remaining portion. Okay, it's very easy. What's the definition of center of mass? You have two masses, which m1 is located at x1 and another mass m2 is located at x2. Then the center of mass by definition is this quantity. Now I will take this entire thing as m1 and then the remaining portion as mass as m2. Okay, so let sigma be the mass per unit area. Sigma mass per unit area of the material of the disc, Okay, so m1 is equal to mass of the smaller circle is pi r by 2 whole squared, that multiplied by sigma. Okay, and where is x1? X1 is r by 2. Yes. Suppose I call this as the origin, with respect to this is at r by 2. Then m2. M2 is the remaining portion, therefore I should, from the area of the entire circle, I should subtract the area of the smaller circle. Therefore, pi into bigger circle area is r squared minus r by 2 the whole squared, that times sigma. And where is it located? It is at some point, it is at the point x2 is equal to, I will call it as x. This is OD. OD is x. Okay. And what is this area? This area I can calculate 3 pi r squared by 4. Now x center of mass is equal to simply m1 is this quantity r by 2 whole squared sigma into r whole squared rho pi r squared by 4 rho I will call mass per unit sigma, I will call it as sigma that into r by 2 plus pi 3 pi r squared by 4 into sigma into x. Okay, that divided by pi r squared rho. The center of mass system is at the origin, therefore it is 0. So we will have solve for this. R by 8 plus 3x by 4 is equal to 0. Therefore x is equal to minus r by 6. So this is the OD is the distance r by 6. Therefore the center of mass of the remaining portion lies along the x-axis at a distance of r by 2 on the left hand side. Okay, so the coordinates of dr minus r by 6 and 0. These are the coordinates of d. Coordinates of d. Okay. So this problem illustrates a simple concept like center of mass, which will be repeatedly coming across. So next problem I've chosen is that is involving some concepts involving moment of inertia, omega, linear velocity, rotational kinetic energy, orbital angular momentum, etc. This is the problem. Okay. Say given a symmetric body, you have been given this. You have been given some information. A symmetric body is rotating about an axis. All that you have been given is its rotational kinetic energy. Its rotational kinetic energy, what you will call it as simply Ke, it has been given. It has been given to you. Then what more is being given? Its orbital angular momentum has been given to you. Now, since the rotational kinetic energy is given, rotational kinetic energy is equal to half I omega square. Remember, this is in analogy with what happens in linear motion, half mv squared. Orbital angular momentum, I omega. Right? These are the things which are given. Then, now calculate what is kinetic energy by L, that is equal to omega by 2. So this implies omega is equal to 2 Ke by L. So, given rotational kinetic, given you are given that a symmetric body is rotating about an axis, and you have been given this data, the value of rotational kinetic energy and the value of orbital angular momentum. From that, if they simply ask you, if they ask you to calculate omega, this is simple like this. Okay, and you can also calculate what is I. I is equal to L by omega is equal to L squared by 2ke. Now, in the case of the first one, when they asked you what is the value of omega, let us say that it's a multiple choice question. Omega is A 2ke by omega is 2ke by L, then B ke by L, then C ke by 2L, and D ke by L. Now, in all the cases, we have ke by L. Sometimes what students do is, they are taught that you need not work out all the problems. Just by eliminating all the wrong answers, you can get the correct answer. And that is true, provided the problem is framed that way. If out of the 4 choices, 3 choices are obviously dimensionally wrong, or then by looking at it, you can come to the conclusion the remaining answer is correct. But in this problem, it is not possible, because the dimensions of omega because omega has dimensions of course, energy divided by L. But there is a proportionality factor that is involved here. Correct proportionality factor is 2ke by L. Therefore, A is the correct answer. So, only way you can do this is by working out. And so, this problem looks very grave at the outlet. Oh, we are given kinetic energy and then we are given orbital angular momentum. How are we to calculate the angular velocity? That is very simple. So, but one needs to know, these are the things, which I keep repeatedly telling. What are the things you should know? The rotational energy is half I omega squared. This is something similar to what happens in a linear motion case. We have seen this analogy repeatedly. Similarly, orbital angular momentum is I times omega. This is something like what happens in the case of linear motion, that F is equal to the momentum of the particle is equal to mass times velocity. And okay, so one should ask whenever say above, what are the concepts tested? That is, what are the concepts which the examiner expects the students to know. And next we will move on to a problem on moment of inertia. So calculating moment of inertia of various bodies is important, and you should practice. And okay, the question is like this. I have 3 rods are there. The 3 rods, each of length L. Therefore, when they are joined like this, you have an equilateral triangle. First thing, P, Q, and R. So, mass of each rod is M. Mass of each rod. Length is L. Okay, length of right. Okay, then find the moment of inertia of the system about an axis passing through its center of mass and perpendicular to the plane of the diagram. Okay, now let us say that the center of mass is somewhere here, C. So this axis comes out of it is not in the plane, I can only indicate like this. This is z axis, let us say that. So you can have your x axis like this, y axis like this, oh my god. இப்போ திருப்பி உடைக்க முடியாதுல்ல சார்? இதை திருப்பி உடைக்க முடியுமா ஆயிடுச்சு? சரி, ஓகே. ஸோ இப்போ சொன்னது மட்டும் இருக்குமா?
ஆடியோ
என்ன பண்ணலாம்? ஃப்ரெஷ்ஷாக பண்ணிட்டுமா? ஃப்ரெஷ்ஷாக பண்ணிட்டுமா?
என்கிட்ட இருக்கும். ஆனால்
அது சிங்க்ரனைஸ் பண்ணலாம் இல்லையா? அதை எதை
இப்போ நீங்கள் பேசுனதெல்லாம் இருக்கு சார், வீடியோவில் இருக்கும். இந்த இந்த கேப்சர் மட்டும் வச்சிருப்போம்.
சரி, நான் சொல்லிடுறேன், அழிச்சுக்கிறேன் பார்த்துக்கலாம். ஸோ வி ஹாவ் 3 rods. They are PQ. இதில் தான் சார் ஒரு ப்ராப்ளம், அழிஞ்சிருச்சுன்னா கஷ்டம். Then the mass of each rod is m, length of each rod is L. So this is a problem on moment of inertia, as I already stated. Then now you are required to calculate the, let us say that you are required to calculate the moment of inertia of this triangle with respect to an axis which is coming out of the plane of the paper. Okay, that is important. Now this is x axis, y axis. Okay, you have to carefully erase this y axis. Right. Now suppose I produce this, it will meet at the point D. This is little d, let us say that OD is little d. So again I repeat, you are required to calculate the moment of inertia of this triangular figure with respect to an axis passing through the center and perpendicular to the plane. This is another axis, Z prime. Right. Now the moment of inertia of I of this very simple problem, what we are going to do is that we calculate the moment of inertia of one rod. That will be equal to the moments of inertia of other 2 rods for that matter, obviously. The moment of inertia is going to be calculated about the point D. Okay, in an axis which is passing through the axis D, which is lying in this plane. Therefore, moment of inertia of so this Z is equal to moment of inertia about O is equal to moment of inertia about Z prime plus, we are going to make use of parallel axis theorem, md square. This distance is d. Okay, so this we have to calculate. Angle DQO is equal to 30 degrees. Therefore tan 30 is equal to tan of 30 degrees is equal to D divided by L by 2. That is equal to 1 over root 3. This implies little d is equal to L by 2 root 3. Okay. IZ is equal to ml squared by 12 plus this m into L by 2 root 3 whole square. This is equal to m L squared by 6. Okay. So I of the system is equal to three times ml squared by 6 is equal to ml squared by 2. Right. Now we will move on to other problem. This again a problem on moment of inertias. Two solid spheres have the two solid spheres are given. This is a problem on moment of inertia. Two solid spheres have the same mass. They are made of materials of different. They are made of materials of different densities. Which one will have larger moment of inertia? Question. Which will have larger mi about an axis passing through the origin? Okay. I1 is equal to, moment of inertia of a sphere of mass m of radius r1 is 2 by 5 mr squared. This is the moment of inertia about the center. So I2 is 2 by 5, since both of them have the same mass but different radii. So I1 by I2 is equal to r1 squared by r2 squared. So what is m1? Mass of the first one, m, is equal to 4 by 3 pi r1 cube rho 1. This implies rho 1 cube is equal to 3m by 4 pi rho 1. Then m2, that is the mass of the second sphere, is again 4 by 3 pi r2 cube times rho 2. This implies r2 cube is equal to 3m by 4 pi rho 2. Right. So, from this, what is r1 squared? R1 squared is equal to 3m by 4 pi rho 1 whole to the power of 2 by 3. So, I will have I1 by I2 is proportional to rho 2 by rho 1 whole to the power of 2/3. Okay, so this implies the moment of inertia is proportional to 1 over rho to the power of 2 by 3. From this you can argue whether the sphere with greater density will have higher moment of inertia among these two spheres which will have higher moment of inertia. That I will leave it you to little bit of think, having done this much. Okay. Now Next problem. This again a simple problem in moment of inertia, but it is good that you know it. Okay, I will do another problem involving torques. Silhouette here, no silhouette here. Let us do a problem involving torques. The physical situation is like this. I have a rod. It's a uniform rod of length AB. It ends labeled like this. Now AB is 10 meters. Right. So this D, the midpoint. Here there is a 30 newtons acting. Now here this distance there is a force of 10 newtons. There is a sorry, not here. The 30 newtons. There is another one at C. Here it is 20 newtons. Okay. So this distance is 2 meters. This distance is 3 meters. And then this point EV will come later. Now this is X. So you are to find the point of application of the force. Point of application is a concept. This concept is like this. In this particular problem, on this rod, two forces are acting. One is at C, another is at D. At C, 20 newtons is acting upwards. At D, 30 newtons is acting downwards. Now, these two forces do not balance. There is a difference of about 10 newtons. Therefore, the point of application is, that particular point is on that rod, where if you apply this difference of 10 newtons, then what is happening is the whatever resultant torque that is produced, that is balanced. Okay, so I will calculate taking moments about C. Taking moments about C. We can take any point, that does not matter. So moment about C is equal to 0, the moment of 20 newtons due to. Then tau D is equal to 30 into 3 is equal to 90. This is clockwise. This is 90. This is clockwise. So I need to find a point X such that at which when 10 newtons acts, this is going to correspond to this 90 newtons. 90, the torque of 90 units. So this gives us X is equal to 9 meters. In fact, one can put wherever you want x newtons, let us say that x newtons at B. Then I have determined x, then overall is 90, torque is 90 units, that should be equal to x into 10. This implies x is equal to 9 newtons. So I can put at B 9 newtons downwards, so that this entire, the earlier system of forces is equivalent to one single force, right? So if on a rigid body various forces are acting and they can create a certain amount of torque, this same amount of torque can be generated by application of one single force at a suitable point. That is the concept that is tested in this problem. Now we will do a problem. Of course, even though we have been using the conditions for translational equilibrium and rotational equilibrium, we will do an explicitly a simple problem. This problem is like this. Okay. There is a tangential force F. The mass of the shell is m and radius is capital R. Now it is rotating in this direction. Now I have a thin spherical shell. We need to find the acceleration of the shell. Now, what are the shell rolls without slipping. Therefore, question to find the acceleration of this shell. Linear acceleration. Of the shell. Now there is a frictional force acting. Frictional force will act here in this direction, because here the motion is like this. Now this is a thin spherical shell which is rolling without slipping. That is the physics part of it. I need to find what is the linear acceleration. First, for translational motion. Translation motion. What are the forces acting along x direction? F plus F, little f friction, F plus F is equal to mass times acceleration. This is one equation. And then for rotational motion, now this tangential force F will there will be a torque on this shell due to the tangential force F. That torque is F into R. This will be in one direction. What about frictional force F? This will also induce a torque on this body. It is in the opposite direction. So this will be a minus Fr is equal to, so this is the total torque. Value of torque is I times alpha. This is m into a kind of thing. This is I into, because there is the shell is rolling without slipping, the condition is So from these two equations, from this second equation is f minus little f is equal to I into a by r squared. Add equations 1 and 3, then straight away the frictional force will cancel. Then I will have 2f is equal to m plus I divided by r squared times a. So this implies a is equal to 6f by 5m. Okay, so I can have this as m plus I value is 2 by 3 m r squared, that is the moment of inertia of a spherical shell, that divided by this times a. So I will have r square and r square cancel, therefore this is how I will have. So what are the things that are expected in this particular problem? You need to realize what are the physical conditions for rolling without slipping. For rolling without slipping, the condition is velocity of the center of mass is same as r times omega. So this you can extend it to acceleration also. We will stop at this stage.